Well, hello and welcome to In the Lab. This is it. This is the first, maybe the last, we'll see how it goes, live in the lab that we are doing in school. So thank you very much. We can see that there are a few of you. There's 20 of you now in the chat, which is wonderful.
20.
Just in case you don't know who I am, you should. But if you don't, I am Mr. Walker.
And I'm Mr. Morris. Hello.
Excellent. So let's have a little look about what you are saying. We have got Mittens the cat is a nice chatter so far.
Archie Edwards.
Archie Edwards is there. We've got Dopey Warrior
Hello,
who
Archie.
says hi. Hi, Dopey Warrior.
Jeremy said hello.
Jeremy has as well.
Yes.
That's very nice. Anyone else who wants to give us a comment or a question? It might be sciencey. It might be not too personal, but it might be about us. You know, use your discretion there. Ask us a question. If we like it, we will answer it
Absolutely.
for you. Give us your comments as well. Put some highs in there. Give us some love. Give us some emojis. Whatever you want, do that in the chat. And while I am having a look at the thread there, oh, Chesko's just come on there. He's just been doing gardening with me. You've made it hi.
He must have ran.
He must have ran. And Mittens the cat says hi again. There's a lot of highs from Mittens. Well, Mr. Morris is going to get ready to do his experiment, and I'm going to stay over here and read out some more of your comments. So do keep them coming.
I will toddle off. See you in a sec.
Absolutely. Goodbye, Mr. Morris. What you can't see, by the way, is that we have lots of sciencey things on the desk here. We've got these here, just to make you feel a little bit more at home, but it's actually out of shot. But never mind, never mind. I'm going to show you this one as well. We've got the nice Newton's cradle. They may feature in another video in the future. And look at this. I know a lot of you haven't actually seen this, but this is a lovely Galileo thermometer. If you're interested in watching videos about the Newton's cradle or the Galileo thermometer, go back into our back catalogue. You will find lots of things covering these and many other topics as well. Let's see if we've got any new comments. Oh, Ben says hi. Archie Edwards has asked us a very, very difficult question. 1 + 1. I can tell you it's 2. Oh no, the question is why is 1 add 1 is 2? Well, that's a mathematical question, so you can ask Mr. Casey about that. My answer is it just is. Hello from Nathan. Hi from Archie Edwards. I'm loving these comments from people. And there's more of you on here, which is absolutely wonderful. I am really enjoying that. Oh yes, we also have a special guest who is with us. We're going to go over right now to Albert Speinstein. Have you got anything to say, Albert? No? What a waste of time that was. Well, back to me then. Thank you very much. We will drop in periodically with Albert just to see if he does have something else that he wants to say. I think if we've not got any more comments, oh, we have actually. We've got Phoebe who says hello. We've got an unpronounceable name that says hi, sir. Hi, Mr. Walker from Mittens the cat. I want to know who Mittens the cat is. I'm very interested there. Yeah, we've got Natural. Natural says hi, Chesko. And you're all saying hi to each other. But there you go. We've got some interesting questions, not all of which will be read out, thank you. But if they are good, we will cover those questions. Now, you might hear in the background that Mr. Morris is making some kind of squirty noises. It's quite interesting. You are going to see some bubbles set on fire very, very soon. He's going to explain the science behind it. He's going to set things on fire. It's going to be fun. But I can tell you safety is an important priority. We have put a red cap over our fire alarm just to make sure that everything is okay. That's not the fire alarm. That's just our gas alarm, which means that we need to turn it off, put the fans on, and then turn it on again, and then we'll be okay. So, as we get our gas prepared, it's live. This is why you're tuned in, isn't it? So that things would go wrong. Be honest. Now, the gas is being prepared. Mr. Morris is back at his station, or he will be in a moment. So we're going to go over to Mr. Morris, and he's just going to explain what he's doing and what's going to happen. So I think it's time to go over to Mr. Morris.
Hello. So just while the gas is sorting itself out, very simply in this bucket here, I have some soap and some water. You can see some soapy bubbles, just like you would wash up your dishes with. What we're going to do is we're going to take some gas from our gas tap. This is methane, so it's a hydrocarbon. And hydrocarbons burn very, very, very well. If you've studied combustion yet in your science lessons, you may have done, they react very well when they react with oxygen. And they produce carbon dioxide and water. But they also make really nice flames. And I am a fan of setting things on fire, it has to be said. So, as soon as I've got my gas on, oh, is everything okay, Mr. Walker?
Oh, we need to test the gas taps. and make sure they're all closed. Which, of
Okie
course,
dokie.
is very important to do.
Fun times. So the idea is we're going to fill some bubbles up with methane and we're going to set them on fire. I'm going to do quite a few times. I quite like doing this. It's really, really cheap. If you don't want to have your eyebrows waxed, you can do this. It's great. Gets them right off. Let me just check my other gas taps over here, just making sure they are all shut. Yes, they're all shut. Shall we try again, Mr. Walker? Where's he gone? We will try again. Okay, some bubbles, not many. Is it back on yet, Hannah? Let's go back to some comments. So, while we're waiting for Mr. Walker to return from wherever he's gone to, let's have a little look. So, Phoebe says, hi, sir. Hello, Phoebe. Who else have we got? Mr. Morris from Mittens the Cat. Thank you, Mittens. I'm not going to read some of these because that's kind of mean. That's kind of mean, dude. Got a few hellos here for our helpers as well. Thank you very much for that one. Very odd question there that, yeah, I'm not going to read that one out. That's a bit of a strange one as well. What's my favourite experiment? Ooh, that's a good question. That's quite a lot, actually. I really like this one because I like setting things on fire. I don't mind telling you that. I also like the one where we distill crude oil because, again, you can set things on fire. If you've ever seen the Rainbow Fizz one is amazing. So you get some sodium hydrogen carbonate and you pour it into a burette with some acid. It's like a really long, thin glass tube. And you'll have some universal indicator in there. And what will happen is as the hydrogen carbonate reacts with the acid, you get red at the bottom, then orange, then yellow, then green, then blue at the top. And you get this like fizzy rainbow in the burette. That's a really good experiment. I'm not sure who's asking about maths homework, but this is probably the wrong forum in which to do that. Maybe email your maths teacher if you're not sure about your maths homework. But yeah, that's one of mine. What else do I like in terms of experiments? I've done so many. I used to really enjoy it when I worked in a real lab, like an industrial lab. We used to analyse all kinds of different things and test them for all different kinds of compounds. I think my gas is working now, Mr. Walker, is that correct? Iffy, he's telling me this, I'll waffle for a bit longer then. Do nerve cells travel in veins or other things? Good question, Ben. Blood travels in veins. Nerve cells have their own set of pathways, so nerve cells are all connected together and they carry impulses around the body. So they don't travel themselves, rather the signals travel down the nerve cells. Really good question. Can we do experiments like this in school? Well, we do experiments like this in school. We do experiments like this in school. We do the one we're going to do in a second in year 10, especially when we look at combustion. We've done it in year 8 for combustion as well. So whenever we get an opportunity really to show off combustion, we love to do this experiment. We love to set the methane bubbles on fire. What's going to happen in the stream? Give us a wiggle of that laptop there, please. Well, I don't know what's going to happen in this live stream, but I do know that I'm going to go and set some bubbles on fire. So, let's go. Hey, look at this. So, we've got some soapy water, and I'm bubbling through some methane. So those bubbles, the larger ones that you can see, they're currently being filled with methane, so natural gas, the kind of gas that you would use in your heating system at home, the kind of gas you might get coming out of your cooker, created from the fractional distillation of fossil fuels, which forms a mixture, because obviously natural gas is one of your fossil fuels. It is also, though, excitingly flammable. Could I have some help, please, Hannah? I know how much you really want to set me on fire. So, if you like the end of that stick, we'll just start off nice and simple, I think. We'll just set one off and then we'll see how it goes. Maybe lights down, sir. That would be great if we could just pop the lights down a little bit just so we can get some... There we go. Nice and gentle. There you go. So hopefully we're going to set these on fire, and we should see that our methane burns really rather nicely. Let me just pop my specs on. Where did I put them? There they are. It's because I left my other ones over there. I got distracted. You ready, Hannah? Go. Ooh, there we go. Good job I did as well, because that just hit me in the forehead. Could I have those other glasses, please? Because I don't like those ones. The clear ones. Thank you. That's better. I'm able to see now. So, combustion. Our methane bubbles burn nicely. We can do some really big ones. Can you smell my arm hair burning already? I can. We can do some really big ones. We can spread them out on the desk. We could write our name in them. You're going to need those, sweetheart. But we're going to fill these bubbles up with some methane gas. Now, sometimes if you do a really big one, you can almost feel it raining, because when methane reacts with oxygen, you do get carbon dioxide and water being produced. Are you ready, Hannah? Move that out of the way. I'm going to try and put this one in the air so we can get a bit of a fireball moment going. Are you ready? There she is. Me bubbles are popping. You ready? You ready? 1, 2, 3. Get it, get it. Hey, nice one. Nice one. I do love this experiment. I do. Is it an experiment, though? An experiment, you're getting values out of it, aren't you? You're measuring variables. This is just a show.
It's a demonstration.
It's a demonstration of combustion.
It's a good one. It's a good demonstration.
It's a very, very, very good one. It's one of my favourites.
The experiment is to see if we can survive this demonstration.
Or if my arm hair can survive this demonstration.
Absolutely.
Right, let's pop some bubbles down on the desk. Just shuffle it out of the way for me, please, Hannah. We'll put some big bubbles down. Just move all out of the way. Go on then. Have a way with it. Let me just move that over there. That's not product placement if I leave that there, maybe. So, this one, it will sit on the desk, it will burn for a little while longer. The bubbles are nice and stable. They do get a bit wet though, so sometimes the excess water can dampen them down a little bit. Oh, nice. There we go. Magic. Absolute magic. So this reaction, the combustion reaction, super useful. We use it to heat our homes. We use it in our cars, in our vehicles. Obviously not with methane, not with gas necessarily. It might be with petrol, if it's a petrol car, diesel, if it's a diesel car. But we use it for the combustion engine. We use it to get around. We also use our fossil fuels, our crude oil, to make things from plastics, for example, polymers, for example. We make all kinds of things from our crude oil. Let's do a couple more, and then we'll go back to Mr. Walker, because I can see him feverishly writing down some comments and questions over there. He's almost bursting to get back in front of that camera and start answering some of your questions. Let's do a really big one. You're going to replace it, yeah? Are you just going to move it up? Cool. So what Hannah's got there, she's got a very long stick, and on the end of that stick, she's got a very tiny splint. So she's lighting the splint in order to light the bubbles. Now, the reason that she's doing it from a distance, obviously, is for safety. While it's very fun, it's very pretty, it's very fun, it's very pretty, you are setting fire to gas, and we know that gas is very flammable, as we've seen. And so, in general, it's usually better to keep it at arm's length, especially if you're as valuable as our students here. Whereas, just set fire to me, it's fine. Ready, Hannah? Yeah. Well done. Right, Mr. Walker,
that was a
back
good
to
one.
you.
Excellent stuff there. Fantastic. So, as we come back over here, we have a few interesting comments. Yes, definitely do keep it to the chemistry guys on the chat. Thank you, everyone. One of the questions was, why doesn't it hurt? Which I assume was about Mr. Morris. I assume you're not asking why doesn't it hurt to watch this programme, because the programme's great, that is why. Why doesn't it hurt? The bubbles burn incredibly quickly, and if you move your hands away fast enough, you're actually moving away from the flame, so you can manage to move quite quickly. But I think you have lost a little bit of...
I've lost some armchair. I have lost some armchair.
Lost some armchair.
Some armchairs. No, I've lost some arm hair. I can smell it more than anything.
We'll
Look,
get you an armchair and
just...
some arm hair as well.
Oh, no, it's okay.
Yeah.
It saves me some money.
So
it's fine.
actually, you can see that the head does get a little bit singed, but it didn't really hurt particularly, did it? Because you
No.
move away from it, and it's quite okay. We have got a lot of interesting comments saying the chemistry's good. Wow, cool, very cool chemistry, and I totally agree with that. You are going to see some interesting physics very soon. So I'm going to leave Mr. Morris to do a few more comments.
Before you go, though, you've
Oh,
just
yes.
been asked there, what is Mr. Walker's favourite experiment?
Oh, my favourite.
So I told them mine. I think
Yeah.
it's your turn to tell them yours.
There's a few. I like the Group 1 metals in water, where you get the different coloured flames as it sets on fire, and it's just a lovely crackle with potassium. And one of my favourites is what I'm about to do, which is quite a coincidence that you've asked me that. It wasn't planned at all. I genuinely love the one that I'm about to do. And Hannah is going to be my volunteer for this one. So I'll leave you in the hands now with Mr. Morris to read out a few more comments.
I'm going to read out a few more comments, indeed. There is a lot of love on the comments for the combustion. And for you, Mr. Walker.
Hooray!
Everyone thinks Mr. Walker's awesome.
Yes, he is.
So, really good one. Oh, it's chlorophyll in all living things. I love this. Whoever, I can't even read it. Whoever that is, Annie War, I think it is. Amazing questions so far. So, is chlorophyll in living things? The answer is no. So, chlorophyll is a pigment. We find it in plants, green plants, and it's what gives them those green leaves. Now, the pigment itself, it absorbs the sunlight for photosynthesis, so it tends to be whenever you get organisms that can photosynthesize, they will have chlorophyll in their cells, usually in little tiny organelles called chloroplasts. So really good question there. Now, Mr. Walker in a second is going to tell you a little bit about his favourite experiment. Are you ready, Mr. Walker?
I am ready.
Oh, he's ready. Amazing. Keep the comments coming in, guys. Keep the questions coming in. Oh, hello, Jeremy. Nice to meet you. To see you again. Keep the comments coming in. Over to Mr. Walker.
Well, this is my favourite experiment. Some of you have seen me come into your lessons to do this because I plead with the teachers to do this, and sometimes they're nice and they let me do it. It is the Van de Graaff generator. If you've not come across it, let me very quickly tell you what's going to happen. As I turn it on, this belt is going to move incredibly quickly. There's a brush inside the dome. The roller is going to brush against the brush, and it's essentially going to cause friction, and therefore the electrons will be flicked off the roller up onto the dome. So we're going to get loads, billions and trillions of electrons building up around this dome. It's going to get extremely negatively charged. Now, I'm sure you know that like charges will repel. They are desperate to get away from each other, but they can't because they're all stuck on this dome until we provide a way for all these electrons to travel down to the Earth. The Earth is massive, and therefore the electrons can get down into the Earth, they can repel each other, and they can spread out in the Earth, and everything's nice and stable again. But we have to provide a route for that to happen. So let me show you what I can do. I will turn it on at the plug. We have it on nice and high. And I must say, before I do this, before I turn it on, we've been very careful with safety precautions. Myself and my victim, volunteer Hannah, we've made sure that we've not got anything electrical on us because it can damage electrical stuff if we're far too close. Now, I'm not going to touch that at all, so even though I've got a microphone on, I'm going to be okay because charge will not run through me. But I've not got a phone on me, and neither is Hannah because she'd get a 3, so she hasn't got her phone on her. And we've not got any medical conditions or implants that it might affect. We just have to be super safe. So I'm ready to turn it on. There goes the belt. Electrons are whizzing up to the dome. We've got trillions up on that dome, and I am going to try and get that charge to get down to the Earth. This ball here is made of metal. If I move it close enough, the electrons will jump the gap to here, straight down through the machine, through the plug, down to the Earth. So I'm effectively going to create lightning. This is what you can see right there. That is lightning, the same as what you see in the sky when the electrons jump from a cloud to the ground or back again. But what if we try and use a different mechanism of getting all that charge down to the Earth? What if we use a living person who might actually be a very good conductor? And here's where Hannah comes in. So let's see what happens when you go close. Let's see if we can see that lightning again. Go for it with one finger. Here we go. In we go. She's going for it. She's going for it. Oh, no, oh, no, I'm kidding. That was just me. Go for it. Go for it. Here we go. In with the finger. Go on, get closer. She can do it, she can do it. Give Hannah some love in the comments. Here we go. Oh, she did get a shot. We didn't see the lightning, but she got a shot. Would you like to do it again? No. Don't be so negative. Negative. Anyway, just to show you there is still a lot of charge up there. Look at that. We have got thousands and thousands of volts, but the current is low, which is why it is a safe thing to do. Now, if I turn it off, I'm always going to decharge to make sure that there's no charge there. We're going to see if we can build up a charge on Hannah. So, Hannah, would you like to position your tray on the floor? All it is a simple plastic tray, the like of which you've seen millions of in your practical experiments. I am going to turn it on. She's going to place her hands onto the dome, and she's going to become an extension of the dome itself. The electrons will build up not only on the dome, but on Hannah's mass, all over Hannah's mass. So there'll be even more electrons because there's more mass for the electrons to build up on. So, if I turn it on, she's not getting a shock, but look at the hair instantly. That's it. Shake your head a little bit. Shake your head. Free those hairs up. All those electrons are building up all over her body and on every single strand of her hair. That means that each hair is negatively charged. See, I told you Hannah was negative. And every single hair is going to try and repel from every other hair. And that's why it sticks out like that. Go on, give us a really good shake, a massive shake, like you're on a shampoo advert. Even more, even more. That frees up the hairs. Look at that. We've got lots of volume at the top there, lots coming out the side. I'm trying not to get shocked here, but if I move a little bit closer, I can actually feel, you can see there that I'm affecting the hairs. I'm getting close enough for some of them to jump to my hand, but not enough to damage the microphone, and not enough to actually give me a shock. We're not getting electrocuted, by the way, because that means killed by electricity. We're just getting a shock. And in fact, I'm not. Well, Hannah might later on, we'll see. So as you can see, I'm getting rid of some of the charge by going close, but I'm not allowing the whole charge in one go to jump onto me. Now, what happens if you step onto the floor at this point, Hannah? Watch Hannah's hair. Watch Hannah's hair. Let's see. She's got to do it at some point. She's looking at me going, no, I'm not going to do it. I'm not going to do it. You're going to have to leave at some point. Here we go. I can turn it off. I can turn it off for you if you want. There we go. And as she steps down, the hair very slowly, in fact, a lot of it is still standing up on end, but it is slowly going down again. Because as she stands on the floor, the electrons can dissipate. They can travel down to the earth. And of course, they're not repelling each other. But there you go. I think we should try something else. Because there is something else cool we can do. We can discharge, and we can try this. I'm going to move the tray, and I'm going to get hold of some nice pie tins. Me and Mr. Morris had some nice pies ready for this experiment. That's why we did it, in the name of science. So I'm going to put them on here. Remember, there's no charge because I've got rid of it. So I'm totally fine to touch it. What do you think is going to happen? You might have seen it, but if you haven't, what do you think is going to happen when I turn this on? Remember, we're going to build up loads of negative charge on this dome. Are we going to suck the positively charged pie tins to the surface, or are we going to see them all fly off instantaneously? What do we think is going to happen? You can have a little think. You can even put it in the comments if you want to, if you're quick enough. Yeah, it could be anything really, couldn't it? If you've not seen this, it's a bit of a poser. Hannah, you may know what's going to happen. Can you remember? Tell us now.
It lets one at a time float off the top and fall down.
Ah, so not quite what I said. It's not going to be sucked, and it's not going to be blown up at once. We've got some suggestions. What do they think?
We've got explode.
We've got explode, thank you.
We've
yes,
got,
yeah.
another one for explode.
Oh, right,
They're going to fly. They'll fly off. They're going to fly everywhere. Someone asked what the electrons could be used for.
Oh.
And something to think about when you come back in a second,
That's
sir.
a good one, isn't it? Nice one. Yeah.
Lots of saying fly off, fly away, explodes.
Fly away.
Let's find out.
I think the explodes is wishful thinking. I don't know if they're talking about Hannah or me or the pie tins when they say explode, but it could be any of those things. Hopefully, nothing and no one's going to explode. Flying off is accurate. And like Hannah said, it's not going to happen instantaneously. It's going to happen one by one. Now, the tricky bit is, and you can put this in your comments if you want, why? Why are they going to fly off one by one? Why don't they all just get negatively charged like the dome and zoom off all in a split second? If you've got an answer, give us that while we watch. And I prove to you it is one by one. It's quite quick, but it is one by one. Here we go. Let's watch what happens. Oh, that was fun. It was like it was snowing pie tins. There we go, decharged. Have we got any suggestions, any ideas yet, sir, as to why they might
We've
fly
not got
off?
any suggestions as to why they fly off.
It's
not
a
yet.
hard
Oh,
one.
hang on.
It's a hard one.
Ben has just said
Yes,
that
go
the
on, Ben.
electrons repel.
The electrons do repel each other. Well, you're quite right. That is why they would leave the surface, because they become an extension of the dome, just like Hannah did when she was standing on the tray. But why one by one? Why don't they all just pick up the charge and then shoop, disappear all in one go? Well, if we've got no more suggestions, I will give you the answer. It's all about gravity. Now, gravity does make a lot of people sad. Did you know that? Well, it gets people down, doesn't it? Anyway, Mr. Morris laughed at that. Just saying, someone laughed at that. But it is about gravity. You see, these pie tins, gravity is holding them down on the top of the dome. Gravity is pulling down. We have to overcome gravity to be able to get them to fly off. Now, the force of repulsion is greater than gravity pulling down, so they are going to fly off. But it's only great enough to overcome the top one. So when we have a whole pile of them and we turn it on, the force of repulsion between this one and this one is great enough to make that one fly off, but they can't all fly off because the weight of the pie tins above is pushing down. But as soon as we've removed this one, whoop, this one's got no pie tin above it. So the repulsion can make this one go whoop and fly off. And that's why you see one by one they all fly off, as the force of repulsion is great enough to overcome the weight of the gravity pulling everything down. And I think that is pretty cool, to be honest with you. Would you like to see one more experiment that we can do with Hannah? It does involve her, if she gets it wrong, getting shocked. So I think that's a yes. I think that is a yes. Oh, and she's like, oh, does it? Does it? Yes, it might. So I am going to move our Van de Graaff generator a little bit closer to the water. Now, normally you wouldn't mix electricity and water, but we're going to do this carefully. We know this is safe to do. So Hannah has to stand on the tray again. We're going to build up some charge on Hannah as she becomes an extension of the dome. Now, if I come in here, I'm going to get a very small trickle of water going. I only want a small trickle so that it's easier to affect. The less water, the less force we're going to need to actually affect that flow of water. So we've got a very small, oh, I turned it off then, very small trickle of water there. Yeah, I think that's good enough. And if I turn it on, we will see what happens when Hannah goes close to the water. But she's not going to touch it unless she wants a shock. Let's see what's going to happen. Keep one hand on Hannah and one hand near the water. So at any point, you can go close to the water with your finger. Oh, look at that.
Yeah, I'm fine.
Look at that. But if she gets too close and her finger touches that water, just go a bit closer again. She says, I'm not touching it. That's all right. But if she does get too close, then all the charge will suddenly go into the water, through the tap, down to the earth. She'll decharge and she'll feel that jump. So we're only getting the water to move towards her because different sides of the water molecule are charged, and we're attracting some of those sides of the water molecules towards her finger. Would you like to touch the water? No, she says no. She says no. And I can't blame her because she would get a shock. But there you go. You've heard of the airbenders. Well, this is a water bender. She is very, very good at doing that. And you might notice the hair is flying everywhere once again. And as we stand on the floor, it very slowly starts, especially if she pushes it, it very slowly starts to dissipate. Last thing we do, discharge it, and we are sorted. That's why that is one of my favourite experiments. I love the Van de Graaff generator. And you got to see it for free. We didn't charge you at all. Thank you very much. And with that, Mr. Morris is going to do more comments, if indeed we have any, and I do hope that we have. So let's go back over there, and I'll see you in a minute.
Thank you very much. Yeah, sorry to everyone that just heard me answer my phone. I forgot I had my microphone on still. I didn't know who it was ringing me. I thought, better answer that. Turns out I don't have to collect the dogs tonight. That's nice.
That's good.
So, yeah,
that's very
if
good.
you heard me, I was organising collecting my pets from my parents.
Lovely.
We've had some really good questions, actually.
Yes, yeah.
One of them then, actually, where's it gone now? Why does the water go to her and not away from her?
Yes.
That was the question that we just got asked.
That is a
Well,
good
that's to do with the chemistry of water itself, isn't it?
It is.
So water, I'm going to draw on this board, I think. Can we see this board? So water's
go
a
for
really
it.
interesting molecule because it's got an oxygen in the middle and then it's bonded to two hydrogens, like that, H2O. We all know that, right? Can we all see that? I hope we can all see that. Now, the thing with hydrogen and oxygen is that oxygen really loves its electrons, and so it will pull electrons towards itself from the hydrogen. And that means that because electrons are negative, our water becomes more negative and our hydrogen becomes more positive. So water itself has a charge. And what that means is if you're charged as well, you're going to attract the water or repel the water depending on what charge you have. Okay? So that was a really good question.
It is. We've got another question. Mr. Walker, the goat of a subscriber. I'm not quite sure what that means, but goat, I do know what goat means. And thank you very much, whoever that was, Choke Commander. Leo Tranter Perkins says, what is your favourite type of science? I do love all science. I have to say, I went and I did biomedical science at university. So I am very much a biology person. So that is I have to say, is my favourite. I love that, especially human biology. So you'll often see me coming in doing dissections and walking around when I know that they're doing them because I love that. What's your favourite science?
Oh, chemistry.
Chemistry, yeah.
I don't do much with these days, though. I do more biology.
Yeah, and everyone's got a different one. Miss Ashley and Miss Salt, I think they like physics the best.
Yeah.
Miss Vernon likes chemistry.
Yes.
Mr. Morris, biology. So everybody's very
Microbiology.
different. Microbiology.
Microbiology.
And Mrs. Hall likes biology too.
She does indeed.
So, you know, we all have a different subject that's our favourite, but we do love to teach all of them, although I don't really teach it, do I, apart from gardening? Haha.
There's some really good questions
Yes.
here as well. Phoebe just asked, why is yawning contagious?
Do you know what? I do know about that.
You do? I know you know that.
Yes, the latest theory about yawning is that you need to cool your brain down. So when you are challenged with something, your brain is working much harder. The neurons are firing much more quickly and your body temperature is going up. Your brain does get very hot when it works. So when you yawn, you're breathing in cooler air than your body, and that's cooling down the blood that's going up to your brain and coming back down again. So you're cooling down your brain. You're literally not bored, but you're challenged. And that's when you start to yawn.
I want to yawn now.
I know. And as soon as you start talking about it, you're indicating to somebody else, that's interesting. There's something that's going to challenge me in the local area. I need to actually cool my brain down, ready to do that. So it does explain why it's contagious, because you're picking up the cue and you're going, I need to get my brain cool, ready for whatever's challenged them. Any more?
Someone's asked, what's your favourite molecule?
Or favourite molecule. Don't you know that's a really tough one? Can I say that I think I'm going to go with a metal, which is not strictly a molecule in a way.
It's not a molecule at all.
It's a clump of atoms with delocalized
It's not
electrons.
a molecule.
But I'm going to go with that anyway. All right, I can't go with that. But you know I love bismuth, and if you want to see my lump
do love bismuth,
wonderful
very true.
bismuth, I've got it in my room. My favourite molecule, because I avoided the question completely, I'm going to go simply with carbon dioxide, because we use it so much in our experiments. We either produce it or we use it as a reactant in something. And it's so key to chemistry that we teach you.
I like a good amino acid.
Oh, yeah. Which one?
Oh, I don't mind.
Any.
Just any amino acid.
amino
I like
acid.
amino acid. Bit of an amine group, bit of an acid group.
Nice.
Zwitter ion. Love a Zwitter ion.
Oh, why not? I think we need to ask what Albert Einstein's favourite molecule is. Let's go over there and see what he has to say. Anything? I don't know why we bothered, to be honest. Anyway, we gave it a go. Any more questions?
So Chesko was asking about the combustion
Oh,
reaction.
right. Yes,
and
it was.
a really interesting question. He said, why would you not create incomplete combustion during that reaction?
Yes.
So obviously, in here, Chesko, we've got plenty of oxygen. So that means that all the methane gets burned in oxygen, because there's lots of it in here. The vents are open, the windows are open. If you were in a situation where there perhaps wasn't as much oxygen, there was a limited supply of that, you would get incomplete combustion. You would make some carbon monoxide, or potentially just carbon by itself. You always make water, but you might make carbon and carbon monoxide. But in here, lots of oxygen. We don't need to worry about that nasty toxic gas, carbon monoxide.
Very good. Very good.
And then we had a couple more questions about the Van de Graaff generator as well. So we were asked, fire is my answer. Yes, fire is my answer. Yes. We've been asked about the dome. So does the dome always have the same charge? Is it always a consistent charge? Does it get like a point and that's done, or does it keep on building and building and building and building and building?
To answer a question you didn't ask as well, you can get different Van de Graaff generators. Sometimes it builds up a positive charge on the dome, sometimes negative, depending how it's built. Now, I believe that one is the negative one, so it will always build up electrons, rather than electrons being taken away and going onto the belt. Will it keep on going on forever? No, it won't. It will get to a point where it can't take any more electrons, because there's so many, they are repelling each other, and they're actually very slowly leaving that dome into the air around the dome. And that's why I could go near Hannah and I could feel that fuzziness around Hannah and her hair started to go down because she was so full of electrons, they were actually leaving very slowly. And there was kind of a field of electrons around her in the air. So it will get to a point where it's saturated and they will start to leave if we don't provide a route for those electrons to jump and get down to the Earth. You did ask another question, though, and you said, I think whoever it was who said it, what's the use? What experiment can we do when we're building up lots of things? How is it helpful? There are various different scientific applications. I don't know a great deal about it, but there will be times when you want to build up a lot of charge for a different science experiment you're doing, and you may use an even bigger version of that to create a huge amount of electrons, which you might then use for creating something else or making a different reaction happen. Or, I don't know, for something else. If you find any answers, I'm interested to know. But I know in theory, you could use it in a science lab for something else. Out in the real world, I'm not sure why you would do that. But of course, electricity and wires is very, very important.
I think you need to give a shout out to someone in those comments.
Do I?
Yes.
Yes, here we
There
go.
is someone in those comments who has been asking for a shout out over and over and over again until now. It's just, please give me a shout out, Mr. Walker.
It's me, Mr. Walker, Jack Davis. Can I get a shout out, please? Oh, you can, because you called me the goat.
Of course you can.
Yes.
Of course you can, Jack.
Absolutely, absolutely. Shout out to Jack Davis, and thank you for watching, even though he's not with us anymore, is he? Somewhere else. And we miss you, Jack, we do. So thank you for watching. Very excellent there. Any more?
Yeah, so there's another question here which was, what can protons, electrons and neutrons be used for apart from atomic mass and atomic number? So the electrons, of course, are involved in reactions, aren't they?
Yes,
They're
of course,
involved in
absolutely.
bonding and creating new substances.
Yeah.
So if you've got the elements, they will combine together, they'll bond together. Depends on what type of element you've got, though, depends on what type of bond you make. So if you've got if electrons being transferred, you're going to get ionic compounds, things like salt.
Yes.
If you get them sharing, you're going to get covalent compounds like carbon dioxide, the one you mentioned.
Yes.
So electrons are used in reactions, chemical reactions. Your protons and your neutrons, they're involved a little bit more in kind of the nuclear end of things, aren't they?
Absolutely.
So you can, if you break apart a nucleus, you can get the protons being released as alpha particles.
Yep.
You can get beta particles, gamma radiation.
And you get isotopes.
And you get isotopes, of course, yeah, isotopes. Same reactions, different masses. Yeah,
Absolutely.
very important.
Electrons, very important in your body as well. It's a little bit more complicated than this, but without positive and negative particles and molecules, your nerves just wouldn't work.
That's
And
very true,
various
actually.
other functions in your body simply wouldn't work. So it's really important that we have electrons moving around so that we get the right chemicals in your body so that everything works perfectly well.
And then we've also had lots of questions about elements as well. So
Ooh.
we've got one which says, what is your favourite element?
Right.
And one that says, what is the most deadly element to eat? Now
Bismuth,
that's
bismuth.
No, it's not.
No, it's not
That's
my favourite.
contentious, isn't
Bismuth
it?
is my
Oh, your
favourite.
favourite one's
Yeah,
bismuth.
bismuth.
What's my favourite one?
I don't know.
I don't think I've got one, you know.
That's sad.
I don't think I've got one.
That's really sad. Oh,
Yeah, I like beryllium because it's
There
got
we
a
are.
cool name, but that's other than that, there's no reason really.
and just a quick shout out there to Isaac, who is controlling all of the stuff. So give him some love in the comments as well, if you would. And Hannah, of course, has helped us massively. So well done to those two who have been behind and in front of the camera. Excellent work. Loads of monarchs will come their way, by the way, and general honour. Yes, Hannah's bowing at the moment for some reason because she's overdramatic. Anyway, we've avoided the question. What's the most dangerous one to eat? Anything that is radioactive is going to be bad for you to varying degrees. And there's a
True.
lot of them.
But it won't kill you quickly though, would it? It would be deadly very quickly. It would take a while.
It would take a long time.
But if it was something like arsenic,
Oh, the fastest one to kill you.
yeah, well, I don't know. It says deadliest, so I mean, what do you think is
I'm
deadly?
going to go with chlorine then.
Chlorine
possibly.
gas?
Chlorine
Yeah, mustard gas?
which is banned now by the Geneva Convention in wars because it was so
It is.
bad that they weren't allowed to release it as mustard gas in the wars. It was so horrific, everybody said, we are not using it. So it has to be bad if it's banned from wars.
We've just had a comment actually saying that apparently boron is the best element, always boron.
Always banned.
Yeah, that wasn't on the feed. That was just personally to me, someone who's watching. So
Yes.
that's nice.
Personally,
Um,
I think it's a bit. I think it's a bit boron.
It's a bit boron.
Yeah.
Yeah, no, I think another member of King staff has clearly logged in and is watching us right now. That's
I
very
agree,
nice.
I agree.
I think arsenic. So the number of people that have died, because they used to put arsenic and lead actually
Yes.
in paints.
Yes, they did. They did.
And in wallpaper hangings,
Yes.
and they used to use it for dyes in fabric because
Yeah.
it was the green dye that was it that killed Napoleon or Napoleon's wife.
It's a theory that it might have been. for
Yeah, it's
Napoleon.
like there's two colours, the most deadliest colour in the world, green because of the arsenic, and
Yeah.
white because of the lead, which of course
Yes.
Queen Elizabeth used to paint her face with.
Exactly. People used it. In fact, George III used it as
Yeah.
a wig powder, and they thought that might be what brought on some of his
Symptoms.
episodes. Yeah.
Do you know that with when
Bit of history.
soap became fashionable,
Yes.
Queen Elizabeth didn't want to buy into fashion and therefore didn't use soap. So everybody else in her Tudor court was smelling beautiful, and she continued to not wash.
Ooh. And she lost all her teeth, so her
She
breath
did lose all her teeth.
was stinking. And anyway, it's a good job she's not around now. She did a good job, though. Anyway, anything else that we've got to say? We've got lots of wonderful comments. Oh, a little shout out to Jamie there, who says she's in the best group. You are in the best group, Jamie, and that was from Brathay. Absolutely right. Well said. Well said. Anything else? This is your last chance to make any comments or questions.
Was
and then
one last one
I think
actually.
that's about it.
How do you know you've got a mixture if you only have the chemical symbol?
The chemical symbol.
Yeah, well, it wouldn't be a mixture, would it, if you had the chemical symbol?
Yeah, that's it,
Unless
really.
it was aqueous. You know how the state symbols,
Yeah,
I suppose.
yeah.
If you
I
had
mean-
one that was solid, liquid, and a
Yeah.
gas, it would all be mixed together.
Somebody might say, well, we've got this chemical symbol and we've got this chemical symbol, and they're mixed together in a beaker,
Yeah.
but you'd have to know that, I suppose. You'd
Yeah,
have to,
well,
you'd
if
have
you
to
had,
be told.
say you had sodium chloride,
Mm-hmm.
aqueous, and then water, a liquid, you would know they were mixed because they're in different states.
Yes.
It
and
wouldn't
that-
be NaClH2O, would it? It'd be two separate
maybe they were
things.
asking, can you write it down? Can you write down the formula of a mixture?
Maybe.
I don't think you can really, can you?
Well, I know who's asked that question, so I'll go and ask them.
Interesting.
I
Very
will go and ask
interesting.
them. So the person asking about the particular question there, go and see your doctor.
Yes. Leo is quite right. He was in the best group in Conway. It's a best group competition. Clearly, all the people who are in Brathay with me like to join in with this live feed. You really are in the best group. I do like that. Excellent stuff. Have we finished?
I'm going to
Are we there?
say there's a couple of questions here about
Go for it.
what inspired you to become a science teacher or a science technician.
Yes, I was a science teacher for a while as
You
well,
were.
so I can take, not here, but somewhere else, I can take that question as well. What inspired me? I really enjoy seeing people learning stuff and enjoying stuff, and that moment of, I get it, that was exciting, that was interesting. I just enjoyed that, to be honest.
I think it's because it was the only thing I was ever really good at when I was at school. Or at least the only thing that I was noticed to be good at
Yeah,
anyway.
yeah.
My science teachers at school were pretty cool. And
Yeah.
I like them.
I do like history, and I do like English literature. I like all sorts of
Yeah,
stuff.
same.
But science it just
I
stands
only started
out.
liking maths
Yeah.
though when I started doing it at
Ah.
college and university.
Interesting stuff.
Hated it before that.
And it's lovely that you're all tuning in. Obviously, you enjoy science to some degree. Maybe we'll do this again. We will see. Give us your feedback afterwards. Maybe even send us a message and let us know what you think about that. We do appreciate your nice, constructive feedback.
We do.
Is that it, sir? Do you have anything
That
else?
is it. I'm all done. I'm all good.
I like it. Well, I think we should go over to Albert Speinstein for the final word. What a final word that was. Thank you very much, Albert Speinstein, who seems to be multicoloured at the moment. Well, at least that's different to what it was before. Well, thank you very much for tuning in. We have really enjoyed you being here. So goodbye from me, Mr. Walker, from Isaac, from Hannah, and also...
Mr. Morris.
Yes, yeah, what a great final word that was.
Thought you were about the Speinstein.
Well, Speinstein as well. He's enjoyed himself as well. So thank you very much for tuning in. Off we go now. Bye.
Bye-bye.